Bismillahirrahmanirrahim. So today we will be having our 12th lecture, right? And we will be discussing more about combinational analysis and design, right? So let's move on. So regarding the circuit analysis, right? So we actually have to determine the behavior of the system, right? Provided we are given the description of the circuit, right? So you have to analyze the circuit, and there are certain advantages which we will be having if we will power on the circuit before analysis, right? So we have a lot of different advantages, right? So that we can analyze the behavior of the circuit, we can analyze the combination of different inputs, and on the basis of that input we can have the behavior of the circuit, right? If for example you have a circuit that has 3 variables, so we will be having 2 raised to power 3, 8 different combinations of inputs. So in the analysis we normally apply those different combinations, and we will be watching the behavior of the circuit, right? But on the other hand, the design analysis, right, you actually are analyzing the flow of input towards the output, right? So as I have mentioned that there is a very thin line between the analysis and the design of the digital circuitry, right? So whenever you are analyzing a circuit, so you might be realizing or feeling that you are performing some sort of design steps, right? And in the same way, when you are performing the design analysis, you will feel that you are actually analyzing your circuit. So there is a very thin line between analysis and the design. So we can say that whenever we are designing a circuit, so we can analyze its design and its behavior, right? So they both complement each other, right? So let's start the analysis procedures, right? So as we know that we can have different type of circuits, right? You can have 2-level circuits, right, where we have 2 levels of the gate arrays, and we can have multi-level circuits, right? So regarding the analysis of the circuits, right, it's easier to analyze a 2-level circuit, right, because we can write the Boolean expression by inspecting that 2-level circuit, right, and we don't have to follow certain number of steps while we are analyzing a 2-level circuit. Whereas when we have to analyze a multi-level circuitry, right, or multi-level digital design, it's not an easy job, right, because you cannot write down the Boolean expression straight away, right, and you have to follow certain set of procedures, certain set of rules in order to have the analysis, right? So here you can see that we have 2 different sort of circuits. So this is a 2-level circuit, right, and on the right hand side of your picture you have multi-level circuitry, right? Right here we have the multi-level circuitry. So you can see that we have 4 levels, right? This is level 1, level 2, level 3, and level 4, right? So there are some other complications which we are not interested at the moment, but we will be discussing those different complexities in the multi-level circuit design at a later stages. For example, you need more silicon area, right? And the propagation rate rises when we have a multi-level circuitry, right? And there are some other complications like fan in, fan out, and so on and so forth. But we are not focusing on those different complications. we are just analyzing or comparing those two different types of circuits regarding the analysis and design, right? So you can see that we have a two-level sum of the products here, right, and a two-level product of the sum here, right? So sum of the products, here we have the products, right, and here we have the sum, right? So here we have product of the sum. First we are summing up and then we are ending them or multiplying them, or we are taking the product of those terms, right? So these are different circuits, right? So these are the steps which we have to follow, right? First of all, you have to identify the number of inputs and the number of outputs, right? And then what we need to do, we need to track or analyze the behavior from starting from the input, and we will end at the output, right? And then at the output, what we will be doing, we will be having the Boolean expression, right? And then we will map that Boolean expression onto the truth table, right? Or you can say we will be determining the truth table, right? And the last bullet, we are not very much interested regarding that point, right? Because we can also have the timing analysis, as we have done some examples whenever we have timing diagrams of different inputs, right? And you can analyze the input on the basis of those different inputs in timing diagrams, right? And the power dissipation, of course, if you have a multi-level circuit, right, so you need more wires, you need a bigger silicon area, and the power dissipation will rise, right? But we are not interested at the moment. We just have to discuss, right? Right. So this is the multi-level circuitry, right? And you can see that in addition to the inputs and output, right, we have some intermediary points, right? You can say that we have a point at the output of each and every gate, right? So here if you look at P1, right, so P1 is the output of the gate having x1, x2 and x5 as input, right? Right. And we have P2, that is x4 complemented, right? So here we have P2, right? We have P2 here, that is complemented, right? And then we have P3 over here, and that is x3 is complemented, right? And we have a P4, and P4 is the AND operation between x3 and x4 complement, right? Or you can say x3 and P2, right? And then we have an OR operation here, right? And we have P4, right? P5, right? And then P6, P7, P8, P9 and P10, right? So as we have to analyze the behavior of the circuit, so we will start from the input, right? And we will move on and we will be tagging the output of each and every gate, right, for the analysis, for the behavioral analysis, right? Then we can also have different types of analysis, like verification, right? So as we have mentioned, right, that the circuit analysis, it actually involves, right, finding out what the circuit does, right, or what is the behavior of that circuit, right? So you know that every circuit, it produces a function, right, and that function has to be represented by some Boolean expression, right? Or you can also represent that function in the form of a truth table, right? So the first step in the analysis is to find the number of inputs and the outputs, right? So here if you look at this circuit over here, we have 3 different inputs, right? And we have one output that is tagged as F, right? So first step, we have to find out the number of inputs and the number of output, right? And then we have to perform some symbolic analysis, right? So we can start from the circuit diagram, right? And we actually get the Boolean expression, right, at the output gate, right? And the intermediate points, right, or expressions are combined, right? So you can see that here at the output of each and every gate we have a Boolean expression, right? Okay. Here we have a y complement, x complement, z complement, and then we have x plus y complement, right? So then what we will be doing, we will be having the final Boolean expression, right? Right? So we can have the Boolean expression as well as we can also draw the truth table. So how we will be drawing the truth table? So you know that we have 3 different inputs, right? And how many different combinations we can have? So 2 raised to power 3, 8. So we have 8 different combinations. So we will be having a truth table mentioning x, y, z, and then we can also have the intermediary outputs, right? And finally we will be having the F. So you can have a circuitry like this, right? Or a truth table like this. We have x, then we have y, and then we have z, and then we can have F, right? So we will be having different combinations, right? So here you can also have if you want to have y complement, right? So you can also have x plus y complement, right? So you can also have a truth table of the intermediary states, right? Right. So whenever we are performing literal analysis, right, so we are actually manually assigning a set of values to the inputs, right? So if we have 3 different variables, so we can have different combinations of those 3 different variables, right? Like for 3 variables we will be having 2 raised to power 3, 8 different combinations of inputs, right? So we will be assigning or focusing on a particular value, and then we will be finding the result, or we will be tracing the results, right? So if, for example, we have an expression like this, x plus x bar y, then we have 1, 2, 3 different literals, right? A literal actually is a variable that can or cannot be complemented, right? So here we have x is complement, second literal, and we have a y that is third literal. So this expression has 3 different literals, right? Right. So if we are focusing on this value, right, for x, y, z 1, 0, 1, so you can see that we have 1 over here, x1, so y 0, so its complement is 1, right? So let me place a 0 over here, right? Right. So here we have 1, 0, 1, right? So this 0 is complemented, we got the 1, so we have a 1 over here, right? So 1 and 1, 1, right? So we have to, this is 0, right? And here we have 1, so this is 0, so we will be getting a 1, right? So this is the behavior of the circuit when we apply this input combination, right? So this is the literal analysis. So we can do the same thing for all other combinations, right? Like you can focus on here, right? If you analyze this input or behavior of this input, right, when you are having this. So this literal analysis is very easy, right? Easy and simple. But imagine if we have 4 variables and we keep on rising the number of variables, right? Or is increasing the number of variables. For example, for 2 raised to power 5, we have different combinations for 5 different variables. So this is a sort of a tedious and tiring task. You have to apply all those combinations and then you will be calculating or computing or looking the behavior of the circuit, right? So as we increase the number of variables, this process is not favorable, right? Then we can also have a circuit analysis, right? And in the circuit analysis, we already have the Boolean expression, right? And we can use that Boolean expression in order to find the truth table, right? For example, if you have function, Boolean function, right? So here you can see that we have output, right? That is a function of input x, y, z. So these are the terms, right? X, y, y bar, z, and then we have x bar, y, z bar, right? So you can see that we have a truth table, right? So as you have 3 different variables, so we will be having 8 different combinations as an input, right? So you can compute x, z, right? Y bar, z, and x bar, y, z bar. That are the terms of that Boolean function, right? So here we will be computing AND operation between x, z. So you can see whenever we have 1, 1, so we have only 1, 1 over here, right? Here and here, right? So we will be having 1, 1. So here y bar, z bar, right? So here we will be having y bar and z bar, right? Here, right? You can see that y bar 0, so z 0, so 0, we will be getting 0. So here z 0 and y 0, so y is complemented, so it will be 1, 1, 1. So we will be having another one here. So here again y 0 and we have y complement, so that will be complemented and will become 1. So 1, 1, 1. So here we have x bar, y, z bar. So you can see if we will be focusing on 1 only, so we have x bar, so that is 1, that will become 1, y as it is, and z bar, so we will be having a 1 here, right? So this is the only one we will be having, and rest of the resultants are zeros, right? So, and then we will be having an OR operation between all those terms. So you can see whenever we will be having any one of the term 1, we will get a 1, right? So here we have 1, 1, 1, so all 0, 0, all 0, 0, right? So we have 2 1s, this 0, so we will be having 1, so this is all 0. So this is the sort of circuit analysis. So you see that we have the truth table on the basis of the Boolean function, right? So we can also have sort of simplification, right? For example, we have a Boolean expression, right? X, Y, Z, and we have 3 different variables, and we have the output or Boolean expression, right? So you can see that we have the f, that is the output, as a function of the input variables, right? And we have those terms, right? This one, right? And this one, and this is the final term, right? So we have 4 different terms, right? And if you have if you remember the min terms, right? So you can always have the idea that these are the M1, M2, M5 and M7, right? 4 terms. So before we just draw the truth table regarding the circuit analysis, but now we can also have the simplification, right? So we can use K-map for simplification, right? So let's have an example, right? And we have to analyze the circuit, right? We have the truth table and we have to move towards the equation, and while doing that we will be analyzing the behavior of the circuit, right? This is the circuitry, right? So what we will be doing, we will be having the test point at the output of each and every gate, right? So here we have test point 1, right? Test point 2 and test point 3, right? And then test point 4 and test point 5. So you can see that at the output of each and every logical operation, that is not and this is the output, right? F1, and that is the OR operation. So at the output of each and every gate we have a test point, right? So these are the number of steps which we will be going through in order to have the analysis, right? So first step is to introduce the test points. So this is the first step. Then we will be implementing the steps B and C. So add a column to the truth table for each test point. So you can see if this is the truth table mentioning X, Y, Z, and these are the 8 different possible combinations, right? And this is the output. So we have introduced test points within that truth table, right? So whenever we move from input to the output, we have to fill the truth table, right? So you can see that if you go back, so at test point 1 we will be having 1, right? Complement of X. So we will be complementing X. So you can see 0, 1, 0, 1, 0, 1, 1, 0. So we will be only complementing the X, right? And if we look at the test point 2, so we will be X complemented, right, ended with Y, right? So this and the AND operation of Y, right? So this 0, 1 because both are 1, right? And then 1 because this one and this one is 1, so we will be having a 1, so 0, 0. So again here we have 0, right? So we will be having Y and this one, right? So here you can see that both are 1, Y is also 1, and this is the complement of X, right? So that is 1, so we have 1, 1, 1, 1, all other are 0, right? Then if we look at the test points 3, then this is the TP2 and Z, they are ended, right? So here TP2 and Z, so we are looking for 1, so we will be having 1, so this is the only one that we will be having, right? So then you can see that if you look at the output, that is F1, so we only have 1 corresponding to those positions. So whenever we have 0, 1, 1, we have output high. Here 1, 0, 0, output high, 1, 0, 1, output high. So we have 3 different terms, right? So if you look at the min terms, so this is X bar, Y, Z, right? And this is X, Y bar, Z bar, right? And this is X, Y bar, Z, right? So we have to write sum of the products, right? So this is the logical expression. So this is the example which you can do at your own, right? So again the process is the same, that we have to tag the test points, right? And then we will be calculating the output at those different test points, right? And we will construct the truth table. Then we will be having the min terms, right? This is the output, and we have a 1 here, so we have X bar, Y, Z bar, 1 here, so X bar, Y, Z, and 1 here, X, Y, Z bar, right? So this is the circuit analysis, right? So before we have the analysis, when we have the truth table, right, and we move to the equation, right, or Boolean expression. So now we have reversed them, right? We have the Boolean expression and we have to move towards the truth table, right? So we have to follow the underlying steps, right? So this is the equation to truth table. So this is the circuitry. So here I have mentioned the number of steps which we followed when we are moving from truth table to equation, so that we can compare. So whenever we have a equation and we are moving to truth table, right, so then we have only 2 steps, right? So we have to write down the cumulative logic expressions, right, at the output of each gate, right? So you can see that these are the expressions, right? And then what we will be doing, we will be using the circuit output, right? So you can see that we have the output here, right? So what we can have the equation first, right, and then we can draw the truth table on the basis of that equation, right? So you can see that we have x bar y z, right? So here x bar y z, and this is ORed with x y bar, right? So we have the equation. So now we have to find out the truth table. So you know that we have 3 variables, and for 3 variables we will be having 8 different combinations of input, right? So we will be putting the values, right, 0 0 0, so we will be getting 0, right, output, and then we 0 0 1 0. So if I will be looking for the 1, so we have 0, this is 1, y is already 1, and z is already 1, so we will be getting a 1 as a result of this, right? So and then we have a 0, right, and a 0, right, 1 complement 0, so we will get 1, right? And then we have other 2 ones here, right? So this is the way out when we have the equation and we are moving towards the truth table, right? So this is the example, right? So you can see that we have the Boolean expressions at the output of each gate, right, as opposed to the test points. So before we have test points over here, but now we are moving from equation to truth table, so we are doing that, right? So you can see that we have the final Boolean expression, right? F2 is the output, so we will be having 8 different combinations of inputs, and we will be computing the output, right? So here if we have A 0, right, 1 0, right, so 1, and then this is 1, right, so this is 0, so 0 1 0, right? So 0 is complemented, it will become 1, and then we have 1, 0 will be complementing, and we have a 1, so this is 1, so we will be having a 1, right? So you can calculate the rest of the combinations, right? So this is the circuit analysis summary, right? So you can see that we have if we have a circuit, right, so what we have to do, we have to first find the inputs and outputs, right? So then we can have two options, right? Two choices. Either we can find the truth table for the circuit, right? And then from the truth table we can find the Boolean expression, right? Or there is another way, like we first find the Boolean expression, and from that Boolean expression we can draw the truth table. So this is the circuit analysis summary. So you can, it's your choice depending on the type of circuit, right? For example, if we have a multi-level circuit, so it's not easy to draw the truth table straight away, right? So first we normally go for the Boolean expression, right? So if we have a two-level circuit, so it's easier to go for the truth table, and then after the truth table we can draw the Boolean expression, right? So now we will be moving towards the design analysis, right? So as I have mentioned that in the circuit analysis you actually are analyzing the behavior of the circuit, while in the design analysis you actually are gauging the flow of different combinations towards the output, or you can say, in other words, you can say that the flow from input to the output, right? So in you can have an idea that they complement each other, right? So let's have a little bit of comparison before going into design analysis, right? So as we know that the design, in order to design a digital circuit, you have to start from somewhere, right? So normally we specify the requirement, right? And then we start, right? And then we end up with the circuit diagram, right? But in the analysis, right, you normally determine the function, right? And then you have different choices. You can go for the Boolean expression, right? Or you can go for the truth table, right? If you go back, so here you first have to determine the input and the output, right? And then it's your choice, depending upon the type of the circuit, you choose the truth table or you go for the Boolean expression, right? Right. And then we can perform different sort of simplifications and so on and so forth, right? Okay, so let's start the design analysis, right? So you have to start from somewhere in order to design a logic circuit. So specifications has to be given in order to design a digital circuit, right? And specification means that the number of inputs and the number of inputs should be known, right? And then you can start from the truth table, right? So after having the truth table, obviously you wish to have simplification, and there are different techniques. You can use the K-map for simplification, or you can use the Boolean axioms in order to have the simplification. But in K-map you have predefined number of steps, right? So you if you have a Boolean expression or minterms or sum of the products, right? So you straight away can map that Boolean function onto the K-map, and you can then look for quads, squares, pairs, and you can have the simplification. But on the other hand, if you have a Boolean expression, right, so you have to use the Boolean laws or axioms. So there are no predetermined number of steps, right, or there is no sequence of steps when you are following the second approach, that is the Boolean simplification by using axioms or laws, right? But when we are using K-map, we have to follow predetermined number of steps in order or in sequence. So this is the advantage, right? So that's why we normally go for K-map, right? Because we know the steps and the order of the steps, right? But whenever we are doing simplification on the basis of Boolean laws, so maybe you think that this is the final expression or simplified expression. It cannot be simplified further, but it can be simplified, right? So this is the problem we normally come across whenever we have simplification, right? And finally, after having the minimized or simplified circuit expression, we have to draw the circuit diagram, right? So these are the steps, right? So here you can see we have 3 inputs and 2 output, right? So we have determined the number of inputs and the number of outputs. Then we derive truth table. So you can have an idea that there is very much similarity between the analysis and the design procedures. So here, when you start the analysis, you also has to identify the number of inputs and outputs, right? And then you go for the truth table or you go for the Boolean expression. So here we drive the truth table, right? And then we perform the simplification, and finally we draw the circuit diagram, right? So here there is one very important point that I must mention, right? So whenever we talk about the logic design, right, or analysis, logic circuit analysis, so there are 2 different type of circuitry we can have, right, regarding the digital logic design. One is the combinational and the other is sequential. So in the combinational circuitry, we normally represent the output as a function of input variables, right? And we don't have to take care of the previous state, so we don't need the memory, right? Whereas when we talk about the sequential, we have to take care of the previous state and we need a memory to store that state. So here we are only considering the combinational analysis and the design procedures, right? So you can have multiple representation, right? So the circuit representation is not unique. You can use, for example, for a Boolean expression 10 gates, and maybe you can represent the same function, maybe less number of gates or more number of gates. So the representation is not unique, right? So then we have to graphically represent, right, the function in simplification process, right? Then we can also use the don't care conditions in order to achieve the maximum possible simplification, right? So this is the example which we already did. So now I have added this example in the context of analysis and design procedure. So you can see that if you talk about the design, right, so we have a BCD to 7 segment display, right? So this is the functionality, right? And you can say this is the specification, right? So if you look here, right, so these are the decimals, these are the binaries, right? So in order to have 5, right, so A, B is not on, off, right, it will remain off, right? C has to turn on, right? D, and then E is off, F is on, and G is on. So this is the 5, right? So here you can see we have the design steps, right? So we have specified, we have to specify the number of inputs and the number of output, right? So you can see that So for 0, right, if you look here, 0, right, for 0, A, B, C, D, E, F has to, all has to, except G has to turn on, right. So if you focus on 5, so you can see that C is on, right, and D is also on, right, because there is an arrow, so, right. So A is also turned on, right. So here A, right, F, G, C and D, right. So if you look at the design steps, inputs and outputs, right, so we have to determine the number of inputs and number of outputs. So if you go back, so these are the output regarding the BCD to 7 segment display, right. These are the inputs, binary inputs, right. So we have 4 inputs, A, W, X, Y, Z, and we have 5 output, A, B, C, D, E, right, F, G. So 1, 2, 3, 4, 5, 6, 7. 7 segments, so we have 7 outputs, right. And then we have to derive the truth table. That is the second step, right. So you can see that now if you consider the segment A for all those different possible decimal values, and these are the corresponding binary values, and this is the output. So this is the input combination, right. So you can see that we have only used 10 values, right. So we can have 2 raised to power 4, right, 16 combinations. So we have used only 0 to 9, 10 combinations. So rest of the combinations are unused. So this is the second step, right. If you look here, drive the truth table. So we have drive the truth table. So before going to the simplification, what we have done over here, we have introduced the don't care conditions, right. So this is, you can say, a step that is already added in the simplification procedures, right. So here you draw the truth table, right, and then you have introduced the don't care conditions, right. So by introducing the don't care conditions, we can have maximum possible simplification, right. So you can see that we have introduced the don't care conditions, right, and we normally introduce don't care conditions in order to have more simplification, right. So if you look here, right, you can see that if we don't use those don't care conditions, we will be left with this pair, and if we group this pair, we will be having 3 literals, right, and that is if you look here, that is Y bar and WX bar. So these are 3 literals, but after the introduction of don't care conditions, we can use that, right, ones along with those don't care conditions by considering accordingly if we have more simplification, right. So you can see if we look here, without don't care conditions, we only are left with this square, right. So as a result of this square, we will have 2 literals, right, but if we consider this quad, right, so we will be having only one literal, right. So this is the simplification, amount of simplification after the introduction of those don't care conditions, right. So we will be first looking for quads. So you can see we have, this is the first quad, right. So we have Y, right, and then again due to those don't care conditions, we have those another quad, right. So these are the ones which are used along with those don't care conditions. So we have another quad, right, and then if we bend horizontally and then again bend vertically, then we will be having that square, right. So as a result of that square, we will be having X bar, Z bar, right? So again here, so here we have used, right, one don't care, right, in order to have that square. And here if you look at the center, right, we have another square, and again two don't care conditions are utilized, right? So those don't care conditions, they help us in order to have maximum possible simplification, right, is the final expression, right? So after the simplification, we will be writing down the final and simplified Boolean expression, right? So after we can have the circuit diagram, right? So this is the same procedure but for the other, right, segment B, right? So you can have the same procedure for all other segments starting from A, B, C, D, E, F, G, right? Because we have 7 segments, so you can then finally draw the circuitry, right? So this is the repetition, right? Analysis versus design. So after having an illusion of both the design procedures and the analysis procedures, so you can see that there is an overlapping, right? But our objectives are different while we are analyzing the circuit, or we are analyzing or we are following the design procedures, right? If you talk about the multi-level logic design, right, so there are certain steps, right, we have to follow, and there are certain precautions, right, or certain things we have to take care of that, right? As I have mentioned, even for the analysis we have a simplified or simple analysis if we have a 2-level circuitry, right? On the other hand, if we have a multi-level circuitry, our analysis procedure is a bit more complicated. So similarly, if we have to design a 2-level circuit, right, so we normally have a very efficient design, right, because we have a simpler Boolean expression, right, and we have few variables, right, so that helps us, right, or that complements our design procedure, right? On the other hand, if we have a multi-level design, right, so that will naturally rise the fan-in, right? The fan-in is, if you have more number of inputs, your fan-in will rise, right? So similarly, you need more silicon area, right, for a multi-level circuitry. Your circuitry will consume more power, right? There are those different issues, right? They also are correlated with the implementation of the technology you are using, right? For example, we can have standard TTL, transistor logic, CMOS logic, right? And we can also use FPGAs, right? Then we have complex programmable logic device technique, right? So it all depends on the technique we are using in order to have the design. But just to mention, right, that we have to take care of those different parameters when we are following or we are going through the design procedures, right? And this is the example, right? This is your homework. You should try at your home. You have to design a Boolean circuit, right, using 2 input AND gate, right, and 2 input OR gate. You can use number of gates, right? So this is the Boolean function, right? This is, you can see this is the output, is a function of input variables A, B, C. We have 3 different input variables, and these are the min terms, right, sum of the products, right? So 0, 5, 6, right? So whenever we talk about the multi-level design, right, so our desire is, our focus is that we should meet the fan-in requirements of the chosen technology, right? And then secondly, we want to have a minimum logic cost, right? Then we have two techniques regarding the multi-level logic circuits, right? One is we can factorize, right? And then we can decompose the bigger Boolean expression into smaller functional expressions. So this is a sort of functional decomposition, right? You can decompose the functionality, right? So this is another example. This is also your homework, right? You have to construct a logic circuit that has a maximum fan-in of 2 for the following Boolean expression, right? So we have A up to G. So this is the output, right? F as a function of input, right? So we have ACF dash ADEF bar BCG plus BDEG, right? So here you have to factorize, right? So you can factorize. So these are, you should try at your home, right? And here we have another example as a homework, right? So here we have to focus on minimum cost logic, right? So you can see we have a Boolean expression that is a function of 4 variables A, B, C, D, and these are the min terms. We can have 16 different possible combinations, right? So this is sum of the products and this is product of the sum, right? So you can have an idea from the sign. This is the summation and this is the multiplication. This is sum of the product of the sum, right? Right. So another example, right? So now come to the NAND NOR design implementation. So as we know that NAND and NOR, they are considered as the universal gates, right? So whenever we try to design a circuit, or we have to design a circuit, we normally try to use all NAND or all NOR gates, right? So let's start from the 2-level design, right? So here we have the circuitry, right? You can see we have 6 different inputs, right? Or 7 different inputs, right? This is the 7th input, and we have to realize that design or convert that design into all NAND design, right? So what is the procedure? First we introduce the bubbles, right? So here we will be introducing the bubbles, right? So we will be introducing bubbles over here, right? So 2 bubbles, they will cancel each other, right? So this is 2 bubbles, they will cancel each other, right? So 2 bubbles cancel each other, in 2 bubbles, they will cancel each other, right? So this is not the bubble, right? Right. So here we have 2 bubbles, right? So this I have to omit, right? So here you can see that we have introduced 2 bubbles, right? 2 bubbles, they cancel each other, 2 bubbles, they cancel each other, and then here you don't need any bubble, right? So 2 bubbles, they cancel each other, right? Here x5, right? x6, 2 bubbles, they cancel each other, and here we have also 2 bubbles, they cancel each other. So if I have a variable, for example a double bar, so I can have a, they will cancel each other, right? So this is, we know from the axioms of Boolean. So what is this, right? This one. if I take this, right? So let me compute this x, right? If I have an OR gate, right? So if I have a bar, b bar, right? So a bar plus b bar, right? So what I can have whole bar, right? Because we know that we have to break the line and change the sign, so that will be equal to a bar plus b bar, and this is the same. So I can replace this with the AND gate. Similarly, I can replace this with the AND gate, right? OR gate with two complements, OR gate with two complements, right? And then how I can have, right? So if I have a dot a whole bar, right? So a bar plus a bar, right? So that is a bar. So I can have an AND gate, NAND gate, right? If I have the input like this, right? So you can have the idea. So then you can see that this is the complement, right? So here we can introduce, so this is the NAND, this is also NAND. So we have all NAND implementation, right? Then what about the NOR, right? So we have to introduce the bubbles first, right? So you can see we have introduced bubbles, double bar, they will cancel, double bar, they will cancel, right? So here double bar, and here again double bar. So let me compute or show what an AND gate with two bars means, right? For example, we have A, B, so we have A bar, this is B bar. So what I will be having, I will have A bar dot B bar, right? Right? So how I can have this, because we have to break the line, change the sign, so I will be having this, right? So that is the same. So I can replace this AND gate with two complemented inputs with the NOR gate, right? So this is the NOR gate, right? So here you will see that we can replace this, right, and this and this, right? And then again for the complement, what I can have, right, A, right, A bar, A plus A whole bar, right? So we have changed the line, break the line, change the sign, right? So instead of addition, I have multiplication or AND operation. Sorry, A bar, right? So I will be having A bar. So we can have, right? So this is the NOT operation. So this is equivalent to, this is the NOT gate, right? So we can have, so you can see that we have all NOR, right? So these are the sometimes it's better to follow certain steps whenever you are performing the design process, right? So these are the steps, right? For example, first we have to realize the function, then we have to convert that function to equation, right? And then we have to implement the circuit, or we have to draw the circuit, right? So you can see that we have already gone through those different steps, right? So this is the summary, right? So today we have analyzed different circuit procedures, right? Circuit analysis procedures, right? And then we have different design procedures. Then we have seen that what are the complications that are involved when we have to analyze a two-level circuit or we have to analyze a multi-level circuit. So similarly, we have also gone through the design procedures regarding the two-level design procedure and the multi-level design procedure, right? And there are different choices we can make whenever we are analyzing a circuit, right? Like, for example, first we have to find out the input and the output, right? And then we can have the Boolean expression, or we can have the truth table, right? So the design procedure, it normally tells us the behavior of the circuit. On the other hand, in the design procedure, we normally focus on the flow, right, from the input to the output, right? And moreover, we also learned that there is a very thin line between the design analysis, right, and or design procedures and the analysis procedures, right? So that's all for today's lecture, right? And I will recommend you to do more exercise, right, from your textbook, right, so that you will be able to understand the next lecture, right? So that's all, and मेरी तरफ से आपको अल्लाह हाफ़िज़, अस्सलाम वालेकुम।